In movies, spacecraft lift smoothly off from Earth, soar seamlessly into orbit and travel between planets, all as a single, unchanging vessel. In reality, however, that's hardly the case. To understand why, we need to start with the fundamental physics behind rockets. Imagine you're sitting on a skateboard holding a heavy basketball. If you throw the basketball backward, you roll forward. This simple action reveals Newton's third law of motion. For every action, there is an equal and opposite reaction. A rocket works the same way. Instead of a basketball, it expels exhaust gases at extremely high speeds backward, and in response, the rocket is propelled forward. We can describe this momentum exchange mathematically. Consider a rocket of mass m moving at velocity v in space without gravity or air resistance. It expels a small amount of exhaust mass, denoted dm, backward at an exhaust velocity v relative to the rocket. By the conservation of momentum, we derive the key relationship. The rocket's mass multiplied by a tiny change in its speed, dv, equals the exhaust velocity v multiplied by the tiny amount of mass expelled dm. Integrating this relationship from the rocket's initial mass to its final mass gives us one of the most important equations in astronautics, the Tsiolkovsky rocket equation. The total change in velocity, delta v, is equal to the exhaust velocity, v, multiplied by the natural logarithm of the ratio of the rocket's initial total mass, m0, to its final mass after fuel is expended, mf. Here, delta v is the total change in velocity. V is the effective exhaust speed of the engine. m0 is the initial total mass of the rocket, fully fueled. mf is the final mass of the rocket, consisting only of the structure, engines, and payload after all fuel is burned. This equation reveals what is often called the tyranny of the rocket equation. To achieve a high delta V, necessary for reaching orbit or traveling to other planets, you either need an extremely high exhaust velocity V or an enormous mass ratio of m0 to mf. For example, reaching low Earth orbit requires about 9.5 kilometers per second when accounting for gravity and drag losses. Even with a high-performance engine where the exhaust velocity VA is approximately 4.4 kilometers per second, a single-stage rocket would need a mass ratio of about 8.5. That means roughly 88% of the rocket's initial mass must be fuel, leaving only 12% for the structure, engines, and payload. An extremely difficult target with current materials. That's why real rockets use multiple stages. Each stage is essentially an independent rocket with its own engines and fuel. When a stage runs out of fuel, its empty structure, tanks, engines, supports, is jettisoned. The next stage ignites, accelerating only the remaining lighter vehicle. For a rocket with n stages, the total delta V is the sum of the contribution from each stage. The total delta V equals the exhaust velocity of stage 1, v1, multiplied by the natural logarithm of the mass ratio from the start to the end of stage 1, plus the exhaust velocity of stage 2, v2, multiplied by the natural logarithm of the mass ratio from the start to the end of stage 2, and so on for all subsequent stages. By discarding dead weight along the way, each subsequent stage operates with a better mass ratio, dramatically improving efficiency. Is adding more stages always better? While staging helps in theory, in practice there are diminishing returns. The biggest efficiency gain comes from going from one stage to two. Adding more stages increases complexity, mass, and potential points of failure. Engineers therefore optimize for the lowest total launch mass given current technology, typically settling on between 2 and 4 stages for most orbital rockets. Let's look at some real-world examples. Falcon 9 SpaceX, a 2-stage rocket. The Merlin engines have an exhaust velocity of roughly 2.8 kilometers per second in the first stage and 3.2 kilometers per second in the second stage. Its theoretical maximum delta V is around 9.6 kilometers per second, enough to reach low Earth orbit. Saturn V, NASA, a 3-stage rocket. Its first stage engines had an exhaust velocity of about 2.9 kilometers per second, while the upper stages reached up to 4.2 kilometers per second. Theoretically, it could achieve over 16 kilometers per second delta V, enabling lunar missions. Soyuz Roskosmos also uses 3 stages. Exhaust velocities range from 2.4 kilometers per second in the boosters to 3.2 kilometers per second in the upper stage. Its theoretical delta V is approximately 9.2 kilometers per second, sufficient for orbital flight. Carrying all the empty tanks and engines to the final destination would be like driving across a continent while towing every empty gas can you've used, highly inefficient and structurally impractical. Thus, staging is not an arbitrary design choice, but a necessary compromise dictated by physics and the rocket equation. While future technologies may reduce the number of stages, the principle of shedding mass remains crucial to reaching space efficiently. So next time you watch a spacecraft in a movie glide from Earth to Mars in one piece, remember, real spaceflight is a game of dropping what you no longer need, one stage at a time.